This is module 2 of chapter 4. In this module, we shall consider a special type of nonlinear equations called the polynomial equation. In module 1 of chapter 4, we have described Newton-Raphson method to find only one root of a nonlinear equation. But in many applications, we have seen that the roots of a polynomial, all roots of a polynomials are required. For example, to find the poles singularity of a function, all roots of a polynomial are required. A lot of direct and iterative methods are available to find all roots of a polynomial equation. In this module, we shall consider two iterative methods to find all roots of a polynomial equation. First, we define a polynomial equation. Let p and x be a polynomial in x of degree n, and a0, a1 up to an are the coefficients of p and x. Then the equation p and x equal to 0 can be written in explicit form as a0 x to the power n plus a1 x to the power n minus 1 plus dot 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 plus an minus 1 x plus an equal to 0. This is the polynomial equation of degree n. Here we assume that all the coefficients a0 to an are real numbers, and a number xi, it may be a real number or it may be a complex number, is a root of the polynomial equation p and x equal to 0 if and only if p and xi equal to 0. And we know that every polynomial of degree n has exactly n roots. If xi is a root of the polynomial equation p and x equal to 0, then p and x is exactly divisible by x minus xi. And if Pn is divisible by x minus xi power k, where k is greater than or equal to 1, but it is not divisible by x minus xi power k plus 1, then xi is called a multiple root with multiplicity k. If k equal to 1, then the root is called the simple root or single root. Now we describe Virga-Vitta method to find all the roots of a polynomial equation. This method is based on Newton-Raphson method described in module 1 of this chapter. Let xi be a root of this polynomial equation. Then x minus xi is a factor of equation 2. It is obvious from the definition of root. And when the polynomial p and x is divided by the factor x minus xi, then we obtain a quotient factor, and that quotient factor is nothing but a polynomial of degree n minus 1. And let the quotient polynomial be denoted by q n minus 1 of x, and which is equal to x to the power n minus 1 plus b1 x to the power n minus 2 up to bn minus 1. And obviously there should be a remainder, and that remainder is denoted by capital R. If the polynomial p and x is exactly divisible by x minus xi, then the r, the remainder r must be 0, otherwise the r is a non-zero quantity. Therefore, we can write p and x equal to x minus xi into quotient polynomial q n minus 1 of x plus the remainder r. If xi is an exact root of the equation p and x equal to 0, then obviously r must be a 0, otherwise r is a very small quantity and close to 0. Thus, the value of r depends on the accuracy of xi. The Newton-Raphson method or any other method may use to find the value of xi starting from an initial guess x0, such that r xi, that means the value of the remainder r at xi equal to p and xi equal to 0. The Newton-Raphson iteration scheme for the equation p and x equal to 0 is xk plus 1 equal to xk minus pn at xk divided by derivative of pn at xk, and this is true for all k equal to 0, 1, 2 and so on. So, this is the iteration scheme to find a root of the polynomial equation p and x equal to 0. This method determines the approximate value of xi. So, for this xi, r is not exactly 0, but as per principle this value, that means the value of r is a very small number. Now, our problem is to find the polynomial, the quotient polynomial q n minus 1 x and r. For this purpose, we compare the like powers of x on both sides of the last equation. That means the equation is this one, x to the power n plus a1 x to the power n minus 1 up to an. This is the polynomial Pn, and right side is x minus xi into the polynomial Qn minus 1 plus r. Comparing both sides, we get a1 equal to b1 minus xi. This is obtained from the coefficient of x to the power n minus 1, and it is nothing but b1 equal to a1 plus xi. From the coefficient of x to the power n minus 2, we obtain the second equation, a2 equal to b2 minus xi into b1, or it can be written as b2 equal to a2 plus xi b1. And from the x to the power n minus k coefficient, we obtain the equation, last equation, ak equal to bk minus xi bk minus 1, or bk equal to ak plus xi into bk minus 1. And lastly, by comparing the constant term, we get an equal to r minus xi into bn minus 1, or r, that is residue or the remainder of the division, r equal to an plus xi into bn minus 1. That means the right hand side terms gives the values of b1, b2, bk, and lastly bn. That means this gives the coefficient of the quotient polynomial Qn minus 1. And from the last expression, that means from an plus xi bn minus 1, we obtain the remainder. Now from equation 3, that means the equation Pnx equal to x minus xi into Qn minus 1 x plus r. We see that Pn xi equal to r equal to bn. We denote r as bn. Therefore, the value of Pn is nothing but the constant bn. Thus, the recurrence relation for b's is bk equal to ak plus xi into bk minus 1, where k equal to 1 to up to n. N is the degree of the polynomial, and the starting value of b, that means b0 is 1. So, this expression gives all values of the constant b1 to bn, including b0. Now, for simplicity, we differentiate the equation 7 with respect to xi. Therefore, we obtain dbk dxi equal to bk minus 1 plus xi into dbk minus 1 dxi. Note that ak is a constant term because ak is given with the given polynomial Pnx. So, derivative of ak with respect to xi is 0. Now, to simplify the equation 8, we use this notation dbk dxi equal to ck minus 1. Then the above recurrence relation for b reduces to ck minus 1, which is equal to bk minus 1 plus xi into ck minus 2. That means this is the recurrence relation for c's, and this one depends on b's and c with lower order. Finally, the recurrence relation of ck is ck equal to bk plus xi into ck minus 1. This is true for all k equal to 1 to n minus 1. So, from this equation we can evaluate all c's, and from equation 8 we can evaluate all b's. Now, to find the Pn dash at xi, we differentiate the equation 6, and it is equal to dr dxi, which is equal to dbn dxi, and this is nothing but cn minus 1 obtained from last equation, equation number 9. Thus, the iteration scheme, the Newton-Raphson iteration scheme 5, equation number 5 becomes xk plus 1 equal to xk minus bn is the value of Pn at xk, whole divided by cn minus 1, this is the value of Pn dash at xi, and this iteration scheme is valid for all k equal to 0, 1, 2 and so on. This method is known as Virge-Beta method to find a real root of a polynomial equation. All the values of bk's and ck's are written in the tabular form shown below. The first row represents the approximate root x0, and 1 to an are the coefficient of the given polynomial Pn, and second row is obtained by multiplying all b's by x0, and all b's are obtained by the first approximate value x0 is x0, that one remains unchanged, 1 remains unchanged, and summation of a1 and x0 is nothing but b1, and sum of a2 and x0 b1 is b2. Similarly, bn minus 2 equal to an minus 2 plus x0 bn minus 3, bn minus 1 obtained by summing an minus 1 and x0 bn minus 2, and last term, that means r or bn is equal to an plus x0 into bn minus 1. Similarly, we obtain the values of c's from the last row 1, c1, cn minus 2 up to cn minus 1. Cn minus 1 is nothing but the value of the first derivative of the polynomial Pn at the initial case x0. So, this table of values is useful to calculate b's and c's, particularly during hand calculation. Now, we consider one example to find all the roots of the polynomial equation using Virga-Vita method. Here the polynomial is a 4th degree polynomial, so it is denoted by p4x, and we assume that the initial root or first approximate root is x0 equal to minus 0.5. So, using the table which is mentioned in previous slide, we calculated the first and second rows, and from these two rows we calculate the values of b's by adding the corresponding columns. That means the values of b's are 1, 0.5, minus 8.25, minus 6.875, and last value is 0.437500, which is equal to b4, and it is equal to p4 at x0. Similarly, the values of c's are obtained by the similar process which is applied in the table, and the coefficient or the values of c's are 1, 0, minus 8.25, minus 2.75. So, these values gives the reduced polynomial qn minus 1, and the last value of c, that means the value of c3 is the value of p4 dash at x0. Hence, by the iteration scheme, the first iterated value x1 equal to x0 minus b4 by c3, which is equal to minus 0.340909. This is the first approximate root of the polynomial, which is near to the initial guess minus 0.5. Now, we apply the second iteration to find the second approximate root. The values of b's are shown in the third row of the table, and values of c's are shown in the fifth row of the table, and therefore, the second approximate value x2 equal to x1 minus b4 by c3, which is equal to minus 0.379351. Similarly, the third approximated value x3 equal to minus 0.381954. Fourth approximate value is minus 0.381966, and note that these two values are almost equal, and hence one root of the equation is minus 0.381966, correct up to 6 decimal places. And from the last iterated table, we can determine the reduced polynomial, that means the quotient polynomial, which is equal to x cube plus 0.618034 into x square minus 8.236068 into x minus 7.854102 equal to 0. And this equation is obtained from the third row of the table. All the values are marked by red color. Now, we find the second root of the given polynomial, starting from the reduced polynomial q n minus 1. To find the second root, we assume that the initial guess be equal to 1.0. So, using the same method, we calculate the b's which are shown in the third row of the table, and fifth row gives the values of c's. Therefore, the first iterated value of second root x1 equal to x0 minus b3 by c2, and it is minus 2.618026. The second approximate value or second iterated value of the second root is minus 2.618032. So, it is seen that x equal to minus 2.618032 is another root. That means, after second iteration we get the second root. And the next reduced equation is x square minus 2 into x minus 3.00003 equal to 0. Now, root of this equation are x equal to 3.00001 and other root is 1. Hence the root of the given equation are minus 0.381966, minus 2.618032, third root is 3.00001 and fourth root is 1.00000. The last root is nothing but 1. The Virga-Vita method is used to find all real roots of a polynomial equation. But this method is not applicable to find the complex root of the polynomial equation. But after modification, this method can be used to find all roots, real or as well as complex. Also, remember that the method is based on Newton-Raphson method. The rate of convergence of Newton-Raphson method is 2. Therefore, the rate of convergence of this method is also 2. Now, we describe another method called Wheatstone method to find all roots of a polynomial equation. The main principle of this method is to extract a quadratic polynomial from the given polynomial Pnx. And it is well known that the finding of roots of a quadratic polynomial is a very simple task. Now we describe Wheatstone method to find all roots of a polynomial equation Pnx equal to 0, where the polynomial Pnx is defined in equation 12. Let x square plus px plus q be a factor, particularly a quadratic factor of the polynomial Pnx, where n should be greater than 2. Let qn minus 2x and m into x plus n be the quotient and remainder when the polynomial Pnx is divided by the quadratic factor x square plus px plus q, and m and n are two constant, that means these are free from the coefficient of the polynomial or the free from any root of the equation. Thus, the polynomial Pnx can be written as x square plus px plus q into the quotient polynomial qn minus 2 into x plus the remainder polynomial p mx plus n. The polynomial qn minus 2x is called the deflated polynomial, and let it be of the form equation number 14. That means this is a polynomial of degree n minus 2. It is obvious that the values of m and n depends on p and q. If the quadratic factor is exact factor of the polynomial Pnx, then obviously the remainder term mx plus n equal to 0. That means m equal to 0 and n equal to 0. If the quadratic factor is not exact factor of Pnx, then m and n are non-zero, but they are small quantities. Thus, the main aim of this method is to find the values of p and q such that the value of m at pq equal to 0 and value of n at pq equal to 0. Since the values of m and n depends on the values of p and q, so we consider here m and n are the functions of the variables p and q. Let pt and qt be the exact values of p and q, and delta p and delta q are the corrections to p and q. Therefore, pt equal to p plus delta p. P is the approximate value, delta p is the correction or error. Therefore, the exact value or true value of p is pt, which is equal to p plus delta p, and similarly q2 equal to q plus delta q. Hence, our aim is to find the values of delta p and delta q such that m of pt comma qt, which is equal to m of p plus delta p comma q plus delta q equal to 0, and similarly n of pt comma qt equal to 0. Now, by Taylor series expansion for two variables, m of p plus delta p comma q plus delta q, which is equal to m at pq plus delta p into first partial derivative of m with respect to p plus delta q into first partial derivative of m with respect to q, and so on, and equal to 0. Similarly, n p plus delta p comma q plus delta q, which is equal to 0. It is assumed that the correction delta p and delta q are small in general. Therefore, we can neglect the higher powers of delta p and delta q, that means the square and higher powers of delta p and delta q can be neglected from the equation, and after neglecting this equation, the above equation become delta p into mp. Mp represents the partial derivative of m with respect to p, plus delta q into mq, which is also the partial derivative of m with respect to q, which is equal to m. Similarly, from second equation of last slide, we get delta p into np. Np is the partial derivative of n with respect to p, plus delta q into nq equal to minus n. So, these are the system of linear equations, and this equation contains two unknown delta p and delta q, and the number of equations is 2. Therefore, using any method we can find the value of delta p and delta q. Now, the delta p and delta q are obtained by solving the above equations 16 and 17, and therefore, delta p is equal to minus m into nq minus n into mq whole divided by mp into nq minus mq into np. Similarly, delta q equal to this expression. Note that the value of delta p and delta q are determined in terms of the unknown quantities m, n and their partial derivatives with respect to p and q. So, these are not the final values of delta p and delta q, but it is expected that in this stage the values of delta p and delta q either 0 or very small quantity. Since the polynomial Pnx is expressed in the form x square plus px plus q into q n minus 2 into x, therefore, we can write or we get the equation number 19. Left hand side is the expression for Pnx, right hand side is the product of the quadratic factor and the deflated polynomial q n minus 2. Comparing both sides, we get a1 equal to b1 plus p. This is obtained from the coefficient of x to the power n minus 1, and this one written as b1 equal to a1 minus p, and from the second term, that means the coefficient of x to the power n minus 2, we get a2 equal to b2 plus p b1 plus q, that is b2 equal to a2 minus p b1 minus bq, and similarly at coefficient of x to the power n minus k, we get this expression ak equal to bk plus p into bk minus 1 plus q into bk minus 2, that means bk equal to this expression. And lastly, we obtain by comparing the constant term a n minus 1 equal to m plus p into b n minus 2 plus q into b n minus 3, that is m equal to a n minus 1 minus p into b n minus 2 minus q into b n minus 3, and similarly a n equal to n plus q into b n minus 2, and after simplification n equal to a n minus q into b n minus 2. So, last two equations gives the values of m and n in terms of a, b and p, q. In general, the values of b's are obtained by the equation number 21. This is a recurrence relation to get the values of b1, b2 up to bn, and this one is bk equal to ak minus p into bk minus 1 minus q into bk minus 2, and for consistent we assume that b0 is equal to 1 and b minus 1 is equal to 0. Thus, with this notation we can write m equal to bn minus 1 and n equal to pn plus p into bn minus 1. These are the values of m and n in terms of b's. Note that m and n depends on b's. It is obvious from equation number 22. Therefore, differentiating equation 21 with respect to p and q, we get equation number 23 and equation number 24. For simplicity, we denote del bk del p equal to minus ck minus 2 for all k equal to 1 to n, and del bk del q equal to minus ck minus 2. This is also true for all k equal to 1 to n minus 1. Thus, using this notation, the equation 23 becomes ck minus 1 equal to bk minus 1 minus p into ck minus 2 minus q into ck minus 3. And from equation 24, we get ck minus 2 equal to bk minus 2 minus p into ck minus 3 minus q into ck minus 4. Note that the equation 27 and 24 are same. Hence, the final recurrence relation for ck is ck equal to bk minus p into ck minus 1 minus q into ck minus 2. This is true for all k equal to 1 to n minus 1, and it is assumed that c0 equal to 1 and c minus 1 equal to 0. Thus, this equation gives all the values of c's. Therefore, the partial derivative of m with respect to p is equal to minus cn minus 2, partial derivative of m with respect to q, which is equal to minus cn minus 3, and partial derivative of n with respect to p is equal to bn minus 1 minus cn minus 1 minus p into cn minus 2, and similarly the expression for nq equal to minus of cn minus 2 plus p into cn minus 3. So, using this notation, we can write the expression for delta p and delta q as this one. Delta p is this one and delta q is this one. So, this is the final expression to find the values of delta p and delta q, and this expression depends on the values of b's and c's, which are given in previous slide. Now, the next improved values of p and q are p plus delta p and q plus delta q. Now, if p0 and q0 be the initial guesses for the unknown quantities p and q, then the first approximate values of p and q are p1 equal to p0 plus delta p and q1 equal to q0 plus delta q. So, this is the iteration scheme to find the first approximate values of p1 and q1. The following table is very useful to calculate the values of bk's and ck's, particularly for hand calculation. The first row of the table represents the coefficient of the polynomial Pnx, and second row is obtained by multiplying b1, b2 up to bn minus 1 by minus p0. Third row is obtained from the same way by multiplying b1 to bn minus 1 by minus q0, and sum of the first column after 1 represents b1, that means a1 minus p0 is b1. A2 minus B0 P1 minus Q0 is B2, and so on. And lastly, Bn is the sum of An minus P0 Bn minus 1 and minus Q0 Bn minus 2. Similarly, the values of C's are obtained by the same technique, and the last rows gives the values of C's, where C1 equal to sum of B1 and minus P0, C2 is the sum of B2 minus P0 C1 and minus Q0, and lastly Cn minus 1 is the sum of the last but one column, that means Bn minus 1 minus P0 Cn minus 2 and minus Q0 into Cn minus 3. The second approximate value of P2 and Q2 are determined from the following equations: P2 equal to P1 plus delta P, Q2 equal to Q1 plus delta Q. Note that P1 and Q1 are the first approximate values of P and Q, and delta P and delta Q are evaluated at this point, that means at the point P1 and Q1. In general, the k plus 1 iterated value of P is Pk plus 1 equal to Pk plus delta P, Qk plus 1 equal to Qk plus delta Q, where the values of delta P and delta Q are calculated at the previous iterated value, that means at Pk and Qk. The iteration process to find the values of P and Q will terminate when both the values of absolute value of delta P and absolute value of delta Q are very small, that means they are very close to 0, that means the amount of error is 0. Now we consider an example to illustrate this method. Here we consider a 4-degree polynomial. Our aim is to find all the roots, real as well as complex root, using the Bestow method. Here we assume that the initial guess for P and Q are 0.5 and 0.5. The first iteration, first row contains the values of A's, second row contains the values of B's with multiplied by minus P0, and third row is the values of B's with multiplied by minus Q0, and sum of the columns represents the values of B's, and similarly we obtain the values of C's by adding the first column, second column, third column, and so on. The last row represents the coefficient of the deflated polynomial q n minus 2, that means the coefficient of the reduced polynomial q is, first coefficient is 1, second coefficient is 1, third coefficient is 0.75 and last coefficient is 1.5. So C3 is equal to 1.5, which is used to the method to find the values of next iterated value of p and q. Hence delta p is equal to 1.978261 and delta q equal to 0.891304. This is the first approximate value of delta p and delta q. Therefore, the first approximated value of p and q, which are the main quantities of the quantitative factor, the p1 equal to p0 plus delta p, which is equal to 2.478261, q1 equal to 1.391304. The second iterated values are p2 equal to 1.90790, q2 equal to minus 2.86999. This is the third iterated values, this is fourth iterated values, this is fifth iterated values, and in sixth iteration we obtain delta p equal to minus 0.000062 and delta q equal to minus 0.000081. Note that these two values are close to 0. That means we can terminate the process or iteration method to find the values of p's and q's correct up to 4 decimal place. Therefore, the sixth iterated values are p6 equal to p5 plus delta p, which is equal to 1.796471, and q6 equal to q5 plus delta q equal to 0.459879. So these are the sixth iterated value of the parameters p and q. Hence delta p and delta q are correct up to 4 decimal places. Therefore, the value of p and q are 1.7965 and 0.4599 correct up to 4 decimal places. Hence, a quadratic factor x square plus 1.7965x, this is the value of p, plus 0.4599, this is the value of q. So this is a quadratic factor, and the reduced deflated polynomial is obtained from the sixth iteration, and the coefficient of the deflated polynomial q are 1, 0.203467, 2.174505. Thus, the deflated polynomial q2 is x square plus 0.2035 into x plus 2.1745, and this polynomial is correct up to 4 decimal places. Therefore, the given polynomial p4x equal to x square plus 1.7965 into x plus 0.4599, this is the quadratic factor extracted from the best of method, and last factor is the deflated polynomial q2x, and this is x square plus 0.2035 into x plus 2.1745. Thus, the roots of the given equation are minus 0.309212, second root is minus 1.487258, and two other roots are complex. The first complex root is minus 0.101765 plus I into 1.471098, and other complex root is minus 0.101765 minus I into 1.471098, where I is the imaginary quantity, this one nothing but root over minus 1. In this module, two iterative methods are described to find all the roots of a polynomial equation. The first method is used to find all real roots, but the rate of convergence of this method is quadratic, and the second method finds all the roots, real as well as complex, of a polynomial equation. And many other direct and iterative methods are available in literature. The interested person may consult with the Learn More section for other references.